Hello, welcome back to this lesson on the second derivative test, and today we are going to bring back implicit differentiation and see how the application of implicit differentiation is utilized with the second derivative test. We're going to go ahead and jump in and look at example number 5 just to get our brains going again on the second derivative test. They say here the function k of x has critical values at x equals -5, x equals -3, and x equals 3.693. The graph of k double prime of x, the second derivative of k of x, is shown in the figure above. And this is really what we want to learn today in this video and in this lesson. For which values of x does the graph of k of x have a local minimum? Give a reason for your answer. Well, we already know that k has critical values at x equals -5, -3, and 3.7 approximately. So in order to determine what it is, if they are a max, a min, or neither, we're going to go ahead and look at the concavity of the function. So we have k double prime of x. So using this information, I'm going to go ahead and just say, what is k double prime of -5? And k double prime of -5, it's a positive value. K double prime of -3, well, that's a negative value. That is less than 0. And actually, I'll say this. This one's less than 0. This is greater than 0. Okay, and how about k double prime of 3.693? Okay, that point's going to be about here. It's above the x-axis. We know it is greater than 0. We want to know which of these has a local minimum. Well, what we just learned was that k of -5, this is concave up. This is concave down. And this value is concave up. So if these are critical values, concave up, concave down, concave up, the first and the last critical value will give us a local minimum. Okay, so we can say k has a local minimum at x equals -5, 3.693 because k double prime, well, actually, I'm going to say these are critical points. I need to establish first that they are critical points. These are critical points, and their derivative, k double prime of x, is greater than 0. All right, so that's the big idea, right, with the second derivative test, is that the concavity will tell me if it is opening up or opening down, and vice versa. If it's a critical value, then that is going to be either a max or a min. Let's go ahead and let's see how implicit differentiation ties into this idea. So first, let's do a warm-up and a refresher on implicit differentiation. Consider the curve defined by x squared plus 4y squared equals 7 plus 3xy. They want us to show that dy dx is equal to 3y minus 2x over 8y minus 3x. So they give us the curve, they give us the derivative, they just say show it. So I'm going to go ahead and I'm going to take my function and I'm just going to implicitly differentiate, and that should match my function. Okay, so I'm going to differentiate. So I have 2x plus 8y dy dx is equal to, and 0 plus, here I have 3 times, and now I'm going to do the product rule. So I have 1 times y plus the derivative of y, so dy dx times x. Okay, I'll go ahead and distribute this. So 2x plus 8y dy dx is equal to 3y plus 3x dy dx. Okay, if I want to implicitly differentiate, I'm going to go ahead and move all of my dy dx's over to the left side. So after I move, we get 8y dy dx minus 3x dy dx. I'm going to go ahead and move this term over to the other side, and I'm also going to move this 2x to the other side. So this gives us 3y minus 2x. We'll go ahead, we'll factor out our dy dx, the derivative of y with respect to x. So we have dy dx is equal to 8, I forgot my values. So 8y minus 3x is equal to 3y minus 2x. And then I'm going to go ahead and divide. So dy dx is equal to 3y minus 2x divided by 8y minus 3x. And we have shown, does it match? It does. Okay, so we have gone ahead and shown that, hey, there is the first derivative. Okay, part B, they say, show that there is a point P with x coordinate 3 at which the line to the curve at P is horizontal. The line tangent to the curve at P is horizontal. Now, when they say that it is a horizontal tangent line, what they're telling you is that the slope is 0. And furthermore, I shouldn't say m, I'll just say that dy dx is equal to 0. Okay, well, I have the slope here, 3y minus 2x, 3y minus 2x divided by 8y minus 3x, and I'm going to set this equal to 0. Now, a shortcut, whenever you're solving a rational function equal to 0, you can just take the numerator. So 3y minus 2x is equal to 0. Because when I multiply by both sides, the denominator is going to cancel out. And then furthermore, they say with an x coordinate of 3. With an x coordinate of 3. Okay, so I have 3y minus 2 times 3 is equal to 0. So 3y minus 6 gives us 3y is equal to 6. And I'm going to go ahead and divide by 3. So we get y is equal to 2. Y is equal to 2. Okay, so I do need a point P. I need to solve for a point P. So I'm going to go ahead and plug that back into my function, and then we're going to go ahead and see what we get. Okay, so our function is, where were you? Up here at the top. Oh, x squared plus 4y. So our x value is 3, right? So I'm just plugging this back into the original function. I'm going to check and see if this point does exist on the function. So we have 3 squared plus 4 times 2 squared is equal to 7 plus 3 times 3 times 2. Okay, so checking this, we get 9 plus 16 is equal to 7 plus 18. So this gives us 25 is equal to 25. Check. Okay, so there it is. We have shown it. And we'll say at the point 3, 2, there is a horizontal tangent line. There you go. Okay, C. Here's where the second derivative goes ahead and comes into play. They say find the value of d squared y over dx squared at the point P in part B. Does the curve have a local maximum, a local minimum, or neither at point P? So I'm just going to go ahead and find the second derivative of y. And that requires, dun 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 dun, the quotient rule. So there's my original derivative. Okay, so I got to go ahead and find the second derivative. So let me copy this down. Second derivative of y with respect to x squared. Okay, so the derivative of the top, we have 3 dy dx minus 2 times the denominator, 8y minus 3x, minus the derivative of the bottom, which is 8 dy dx minus 3 times the numerator, which is 3y minus 2x, all over the denominator squared. So 8y minus 3x quantity squared. All right, so I have the second derivative. Now what they want to know though, does the curve have a local maximum, a local minimum, or neither at point P? And again, the point P that we found in part B is the point 3, 2. So what I'm going to do is I'm going to evaluate the functions at 3, 2. So this is d squared y over dx evaluated at 3, 2. So I'm going to plug this in, all my x's and all of my y's, okay? So I have 3 times dy dx. Well, at that point, it's 0. dy dx there is 0. So 3 times 0 times negative 2 times 8 times y. That's 2 minus 3 times 3. Okay, minus 8 times 0 minus 3 times 3y, that's 2, minus 2 times 3, and that's my x value. And again, all I'm doing, right, is I'm just going through and I'm plugging in 3 for x, 2 for y. Okay, all of this is over 8 times 2 minus 3 times 3, and that's squared. Okay, so we're going to have to go ahead and kind of clean up. This is where your computation comes in handy. 3 times 0 is 0 times negative 2. So we have negative 2 times, looks like 16 minus 9 is going to give us 7. Okay. Minus 8 times 0, that's a negative 3. And then we have 6 minus 6, that's also a 0. Okay, over in the denominator, 16 minus 9, that's 7 quantity squared. So we get negative 14 over 49, or this would be negative 2 over 7. Okay, so what does that tell us? What does that tell us? Well, that is less than 0. That's less than 0, which implies that this is concave down. So at point P, there is a local maximum. There is a local maximum. So we can say at 3, 2, there is a local max because dy dx is equal to 0. And the second derivative is less than 0 at this point. Okay, and there you have it. That's how you use implicit differentiation along with a second derivative to tell if a point has local extrema. So let's go ahead and look at example 7. Here's just another iteration of what we were doing, except part C is kind of a new wrinkle. So we're asked to go ahead and consider the curve 6x minus 3xy plus y cubed is equal to 40. Okay, so again, I'm going to go ahead and do implicit differentiation. That's step 1. I just want to verify the slope. So I get 6 minus 3 times, I have to do a product rule here. Looks like we have y plus dy dx times x plus 3y squared dy dx, which is equal to 0. Okay, so we'll go ahead and distribute. Okay, I'll move my non-dy dx terms over to the other side. So we get 3x dy dx plus 3y squared dy dx is equal to, looks like 3y minus 6. Factor out the dy dx, and we get 3x plus 3y squared is equal to 3y minus 6. We can go ahead and divide, and we get dy dx is equal to 3y minus 6 over 3x plus 3y squared. And you'll notice that this function, this answer here, it doesn't match the slope that I'm given. However, if I go ahead and factor out a 3 times y minus 2, that's our numerator, and in our denominator we have 3 times x plus y squared. Okay, so these 3's cancel, and we get y minus 2 over x plus y squared. However, looking at this, this does not match what we wanted. We wanted y squared minus x. So one of my x's needs to be negative. I forgot to distribute the negative here. Negative 3. So then this is going to be a negative 3x here. Negative 3x. So then this is a negative 3x. Negative, negative. We have a negative x. And we get y squared minus x. There we go. Okay, verified. All right, so we want to go ahead and we want to, for part B, show that the curve does not have any horizontal tangent lines. Well, again, in order for the curve to have a horizontal tangent line, dy dx has to be equal to 0. So I'm going to go ahead and I'm going to set my dy dx again, which is y minus 2 over y squared minus x equal to 0, and I'm going to solve. So this gives us y minus 2 is equal to 0, which means y is equal to 2. So our curve will have a horizontal tangent line when y is equal to 2. However, if I go ahead and I utilize, again, my original function, so 6x minus 3x times y, here I'm going to plug in 2 plus 2 cubed is equal to 40. If I go ahead and simplify this, this gives us 6x minus 6x plus 8 is equal to 40, which gives us 8 is equal to 40. So I just took this y equals 2, I plugged it in, and you'll see that the x's cancel and we have a statement 8 is equal to 40. Well, this never happens. So therefore, we do not have any horizontal tangent lines. Okay, so we'll go ahead and write this conclusion. There is no point where y is equal to 2. Okay, comma, so there is no horizontal tangent line. All right, C. Show that the curve has a vertical tangent line when y is equal to negative 2. Okay, so I'm going to go ahead and I'm going to plug in y equals negative 2. Okay, and since I want a vertical tangent line, again, this is when the denominator will be equal to 0. So dy dx is equal to some number over 0, where it's undefined. So this is going to be y squared minus x is equal to 0. So if I go ahead and solve this, we get x is equal to y squared, and my y value is negative 2. So x is equal to 4. Okay. So I have shown that there is a vertical tangent line at this point. So vertical tangent line at x equals 4, y equals -2. But I need to show that this point exists on the curve. So I'm going to go ahead and plug this in. So I have 6 times 4 minus 3 times 4 times -2 plus -2 cubed equals 40. And I'm going to go ahead and check to make sure that this computation is valid. So we have 24 plus 24 minus 8, and is that equal to 40? Yes, it is. 48 minus 8 equals 40. Okay? All right, example 8. Example 8. All right, example 4. The function y equals f of x has a differential equation dy dx is equal to x minus 4 over 3y squared. It is known that y of 4 is equal to 1. They say find the value of the second derivative when x is equal to 4. Does the graph of f of x have a relative minimum, relative maximum, or neither at this point? Give a reason for your answer. So what we're going to go ahead and do is we're going to first do what they say. They say find the second derivative when x is equal to 4. So I'm going to go ahead and calculate the second derivative of y with respect to x squared is equal to, derivative of the top is 1 times the bottom, 3y squared, minus derivative of the denominator. So we have 6y squared, sorry, just 6y, dy dx times the numerator, x minus 4. And then all of this is over 3y squared. Okay, now we do want dy, the second derivative of y with respect to x squared, we want this evaluated at a point. Now they gave us a point here. That should be squared also. Okay, and they say for x and y that it's 4, 1. 4, 1. So I'm going to go ahead and plug this in. I'm going to plug these values in. So we get 1 times 3 minus 6 times dy dx times 4 minus 4. So that's going to go to 0 over 3 times 1 squared, which is just 1, and then all of that squared, which would be 9. So since this goes to 0, again, I don't have dy dx, and we're going to have to check that in a moment, but this should give us 3 over 9. 3 over 9, which that is a positive value, greater than 0. So we know that the graph is concave up. Concave up. Okay? So if this is an extrema, then it's going to be a relative minimum. But do I know that it's a relative extrema? Remember, you do need to go ahead and check first. What is dy dx? I have to verify at the point 4, 1. At the point 4, 1, I have to show that this is 0. So I have 4 minus 4, it looks like it, yep, over 3 times 1 squared. This just gives us 0. Okay, so it is a critical value. I have showed the concavity, it's concave up, so that means that this is a relative minimum. So we can say, I'll say here, f has a relative minimum at 4, 1 because dy dx is equal to 0, and the second derivative with second derivative of y with respect to x squared is greater than 0 at this point. At this point. Okay? There you go. All right. B is similar. They just give you a new point. They say the graph of f of x also contains the point 1/2 cubic root of 57 over 2. Is this point a relative minimum, a relative maximum, or neither? Well, remember, the first thing that you have to check is you have to see, is dy over dx, is this 0? If not, then all bets are off. So let's go ahead, let's check dy dx at this value. So we have, it looks like 1/2 minus 4, I mean that's not 0, over 3 times the cubic root of 57 over 2 quantity squared. I don't know about you, but I just know for sure that's not 0. Okay, and if that is not 0, then this means not a critical point. Okay, so we can say f has neither a relative min or max at 1/2 cubic root of 57 divided by 2, because dy dx does not equal 0 at this point. Okay, there you go. All right, very last example. Example 9. They say let dy dx equal 4x minus 3y be the differential equation for the function y equals g of x containing the point 0, 1. They say find an expression for the second derivative in terms of y and x. So what I want to go ahead and do is I have to implicitly differentiate this. So the second derivative of y with respect to x squared, this is equal to 4 minus 3 dy dx. And I'm going to go ahead, they want it in terms of x and y. So I'm just going to substitute back what dy dx is. So 4 minus 3 times 4x minus 3y, which gives us 4 minus 12x plus 9y. And there is my second derivative in terms of x and y. Okay, all I did was just substitute this derivative back in. Okay, and then they say discuss the concavity of the function y equals g of x in quadrant 2. Okay, so it's important to note in quadrant 2, all x values are less than 0. So all x's are negative and all y values are positive. So if we go ahead and we look at the second derivative, if I bring this back up, this is 4 minus 12 times x plus 9 times y. Well, this value right here, this is going to end up being positive because I have a negative times a negative, and then here 9y, that's a positive times a positive. All of this is going to be greater than 0. So we can go ahead and say G is concave up in quadrant 2. And there you have it. That is it. All right. In this video, we went ahead, we discussed the second derivative test with regards to implicit differentiation. We also worked more with implicitly defined functions and curves. Give me a thumbs up, like the video, subscribe for more math videos. See ya.